system of linear equation, but now previously it's order 1, but now it's order 2. But obviously, I mean, you have no idea how to solve it, okay? But now let's rewrite this thing, okay? Rewrite this thing, okay? Let's try to write like y yn plus 1, yn plus 2, blah, 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 like that, okay? So, yn plus 1, what is yn plus 1? Okay, let's represent y1 prime, okay? y1 prime as yn plus 1, y2 prime as yn plus 2, and y blah blah blah, yn prime as y2n. Okay, so we introduce n additional equations here. Okay, n additional equation. Those equations obviously looks easy, right? Okay. With that, with the help of these additional variables, what you can do with the original y1 double prime, y2 double prime, blah blah blah, okay, is that, okay, the y1 double prime, okay, becomes yn plus 1 double prime, right? Because like we know like y1 prime is like put it out. Yn plus 1 is y1 prime. Yn plus 1 is y1 prime. So yn plus 1 prime is y1 double prime, right? Right? Look here. We want to represent y1 double prime. So y1 double prime is basically yn plus 1 prime, right? So you can write like y1 double prime as yn plus 1 prime, right? So this originally is order 2. Suddenly it becomes order 1, right? Suddenly it becomes order 1. And then, okay, you have blah, 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 blah. Okay, the first half is pretty much the same. It's pretty much the same. But the second half, when it involves y1 prime, y2 prime, blah, 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 yn prime, you rewrite it into yn plus 1, yn plus 2, and so on to y2n. Okay? So, you can do that for all the n original formulas. And once you finish this conversion, you will be surprised to see that, okay, the original, like the order 2 system of linear equation suddenly become a bigger system of linear equation, but now it's order 1. Okay, it's order 1. So if you write it like the whole thing, okay, if you let y1 to be like this, y2 to be like that, okay, y1 to be from y1 to yn, the vector y1 to yn, y2 to be the vector from yn plus 1 to yn, then you can write it in the block format. Okay, in the block format. We talk about this block format like a linear equation, a linear algebra, like I believe it was the chapter 2, right? Chapter 2, long time ago. So you can see, okay, this column, okay, the top one is y1, the bottom one is y2. Okay, and it will become this thing. Okay, look at this. The upper left corner is nothing, right? So it's all 0. the upper right is identity matrix. Lower left, lower right, basically is A and B. I mean, A basically represent this. B represent like whatever like your Bij basically, which was originally like A. Okay, times Y1, Y2. So this is a technique that allows you to convert like a second order system of linear equation, system of differential equations into first order, a bigger one, okay, obviously, like, but it's still like what the first order system of differential equations. And with this, okay, at hand, I mean, now you are able to use like whatever like we have learned. How do you solve like the first order like a system linear differential equation like to solve this? It's just a little bit bigger, but basically like the idea is nothing. Okay. So basically, like this is an example. Okay, but I mean, this example, I mean, it even provide like initial conditions. But I will not go into the detail because this obviously involved like because like originally it's 2x2, okay, but now it involved like a 4x4 matrix. Okay, a little bit big. It takes some time to solve it, but you get an idea. Okay, I will not compute this one for you, but the calculation, okay, is pretty much straightforward. Okay, if you know how to do like the previous 2x2 example, this 4x4 basically is just logical and it takes all the time, but the idea is exactly the same. And it's from a textbook, like 319, page 319. I mean, if you don't know how to solve it, check out the textbook by yourself. Okay. So we quickly went over section 2. I mean, as I said, like some of the concepts in that section may be covered by another class, okay, but at least there's like a decent part of material that is like related to linear algebra, which is actually kind of interesting. Okay, so that's why I spend a little bit of time, okay, to discuss about that section. Basically, as I said, like just two concepts, okay, that I want to convey. Okay, then we are done with like section 2. So we move on to the section 3. Okay, the diagonalization. Okay. So an n by n matrix A is said to be diagonalizable if there exists a non-singular matrix X and a diagonal matrix D such that X inverse AX equal to D, where D obviously is a diagonal matrix. I mean, there are only like elements in the diagonal that are non-zero. And we say that X diagonalizes A, okay, if this is the case. So, after we have this definition doesn't need to, do not need to prove the definition, we know, right? But immediately we have a theorem, okay? An n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. How do you prove that? This is if and only if, right? This is if and only if. So we need to prove like actually both ways. So let's maybe let's start with like a simple direction first. Okay, we start with a simple direction. Okay. So A is diagonalizable. Okay. A has n linearly independent eigenvector. Okay. So according to the definition, A is diagonalizable, means there exists an X such that X inverse A X equal to D, right? Where D, you know, is a diagonal matrix. Right? Right? According to the definition from this statement to here. Right? Okay. Then if you try to, multiply, because X is non-singular, okay? If you try to multiply X from the left-hand side on both sides, what you get is AX equal to XD. Is that right? So far so good, right? I'm not changing anything, I'm just multiply X on the left hand side, on both sides. Right? And then, let's consider this X, Okay, let's write A. Let's now try to take a closer look of X. Okay, take a closer look of X. X is n by n matrix, right? We know that, right? X is n by n matrix. Okay, let's try to consider this X by its columns. Okay, obviously X is formed by some column vectors, right? Let's call these are the columns of X. So let's call this one X1. Let's call this one X2, okay? Xn. This is X, right? I'm just, trying to, visualize X, make it a little bit big, and try to represent the X by its column vectors, right? Should be very easy, right? So with the similar, idea, okay. So this is X1, X2, Xn times the diagonal matrix, right? Right? I'm not changing anything. I'm just trying to represent X by its, column vectors. Okay. We can actually go one step a little bit further. Okay. What is that diagonal matrix? The diagonal matrix is pretty much. It is also n by n, but all the other parts are zero. So let's just represent this as D1, D2, Dn, right? And all the other parts are zero, right? Right? Any question about what I just wrote? Should be straightforward, right? Okay. Now, okay, because you know how to do matrix multiplication, right? Okay. If you take a closer look at the right-hand side here, when you multiply this X with that diagonal matrix D, what happens is that this thing is going to be, the first column becomes, D1 times X1. The second column becomes D2 times X2. The nth column becomes Dn times Xn. Right? Right? I mean, you can verify that by yourself. Right? Okay. And then, okay, what does that mean? A times this equal to this. Okay, because the first column is actually A times the first column here. You get the first column here. If you still remember the matrix multiplication element, like an elementary concept, okay, A times this one equal to this one. So actually, it actually means A times the first column equal to this first column. A times the second column equal to the second column, and so on. So it actually tells you A times X1 equal to D1 X1. A times X2 equal to D2 X2. A times Xn equal to Dn Xn. In other words, okay, now you see that obviously these di's are the eigenvalues And those x1, x2, and so on, those vectors, well, column vectors, are the corresponding eigenvectors, right? Based on the definition of eigenvalue and eigenvector, right? And then previously we have talked about that, like the eigenvectors, they are linearly independent. I mean, if you check about that. I mean, so it basically just tells us that these x1 to xn, they are eigenvectors and they are linearly independent. So from left hand side, we get the right hand side. Right? And another